All right, well, welcome back to another calculus lecture video. In today's lecture, we are going to introduce the concept of a limit. And one could say that this is probably the most important sort of basic concept in calculus. It's really the thing that makes everything go round. So where I want to start off with this is, and I want to motivate this a little bit. So the idea here with limits, we want to study and the way that I'll phrase this is we want to study the local behavior of functions. And what I mean by this is if I draw a graph here, so maybe we'll draw it over here. I'll draw this somewhat large. So, I can draw a graph that does something like this. And I can look at it, I can look at this picture sort of holistically and say, okay, well, as I go off to the left, it goes down to negative infinity. As I go to the right, it goes to positive infinity. But what I actually want to do is I want to pick out particular points and zoom in on that behavior. So something like this. I want to pick a point and look locally around this point and get an idea of what the function does around that point. So as an example, suppose I have a function, so suppose f of x is a function with the graph, I don't know, something like this. And I have a removable discontinuity at a particular point. Let's say this is maybe -1. I don't care. It doesn't really matter what we choose there. So let's suppose I have this function. Well, you can look at this function and say, okay, well, as I'm sort of, and maybe we'll say this is the height of 1 here on the y-axis. As I'm moving along the line, it really looks like I should just be attaining this value, that's outside of the circled point when I get to -1. But instead, I jump up here. So really, locally, I want to zoom in on this and say, okay, well, here's my function. And I really want to say, I want to quantify the idea that the function should in parentheses or in quotation marks, should be attaining this value. So we want to quantify, or qualify maybe. Well, we'll say quantify. I think this is actually a quantity. We want to quantify what f of x should be doing. And in order to say what f of x should be doing at a particular point, so we want to quantify what f of x should be doing at a particular point, and in order to do this, what we do, in order to do this, we look around that point. But we don't look at the point. Not at the point. Because we don't care what's happening at the point, because we know something that we don't want to happen is happening at that point. We want to know what should be happening. And so we're going to examine the local behavior, what's happening around the point, but not at the point. So this is the idea of a limit. And so now let's go ahead and formally introduce the definition and the notation of a limit. So definition we say that, and here this is, I'm going to write out a statement and then say, and put some notation with it afterwards. So the following statement is expressed in the notation that I'll write. The limit as x approaches, again, this approach is sort of meant to convey this local behavior, this what's happening around the point. We say that the limit as x approaches a point C of f of x. So the limit as x approaches C of f of x is equal to L, and right, the notation that we use is limit as x approaches C of f of x equals L. So if I ever write this notation, you read the notation as the limit as x approaches C of f of x is equal to L. That's what this means. So we do this if the distance, the absolute value of f of x minus L. So here we think of absolute value as if I take, a difference of two things and then slap absolute values around it, what I'm really measuring is the distance between these two numbers. So the distance between f of x and L, using this absolute value notation, can be made arbitrarily small, that is as small as we like, by taking x sufficiently close to C. Sufficiently close to C. And I will also clarify that is by taking the distance between x and C sufficiently small. So what's the idea here? The idea is that the limit as x approaches C of f of x is equal to L if the following is true. Let's say I want to make the distance between f of x and L very small. Then it should be possible to find a value of x which is very close to C such that this is as small as I like. So maybe I want this less than some parameter epsilon, then I would take this quantity less than delta, maybe which depends on epsilon. This is the typical way that you speak about this if you want to do this more generally. But the intuitive idea is that if I want to make these two quantities close, it is possible to do so by making these two quantities close. Okay? So that's very abstract in a sense. So let's maybe do a proof. We're not going to do very many proofs in this course, but I do want to do at least one in which we sort of demonstrate how this definition and how this idea works out. So for a proof using limits, let's do the following. So yeah, proof using limits. This is one of the only proofs we'll do in the course. So using the definition of a limit, show that the limit as x approaches 2 of 5x minus 3 is equal to 7. Well, so how would I use the definition of a limit to prove that this equality is true? Well, let's look at, and what's the quantity that we're interested in? We're interested in the distance between f of x and the limit 7, or this value 7. So let's look at f of x minus 7. Well, let's just start by doing some algebra. So we have the absolute value of 5x minus 3, so that's my f of x, minus my limit 7. This is equal to, well, let's just combine the 3 and the 7. This is 5x minus 10. And then notice what I can do is I can factor out this 5 from both 5x and from 10. So this is going to be 5 times the absolute value of x minus 2. Well, notice that what I have in my problem, I have the limit as x approaches 2, and I have the distance between x and 2 right here. So if we want to make the absolute value of f of x minus L, which is 5x minus 3 minus 7, small, then we can do so by taking x close to 2. For instance, if we want, say, the distance between f of x and L less than or equal to, oh, I don't know, 1 over 100, then choose x equal to 2, so we're going to take it really close to 2 and then add on a little bit. 2 plus or minus, we could be above or below 2, it doesn't matter, plus or minus maybe 1 over 500. Then, well, if I just choose x to be this, then we've already seen that the absolute value of 5x minus 3 minus 7 is equal to 5 times the absolute value of x minus 2. Well, if x is equal to this guy, then the absolute value of x minus 2 is equal to, well, we have our 5, and then the absolute value of plus or minus 1 over 500. That is just 1 over 500. And boom, look what we've done. We've said that as x gets close to 2, it's, 2 plus a little smidgen right here, I've made my quantity f of x minus L very close to 0. I've made it less than 1 over 100, as small as I like. And you can see that if I were to make this 1 over 1,000, I could take this 1 over 5,000, so on and so forth, and I can make this quantity as small as I like by taking x sufficiently close to 2. That is, by taking this little piece that I'm adding on very, very small. And we're done. That's all we needed to say. So, therefore, the limit as x approaches 2 of 5x minus 3 is equal to 7. And typically when we end a proof, we put a little box right there. In your homework, I have you do this with a different kind of function. The main thing to say is that you can take the f of x minus L, the absolute value of those things, and write it in a form which depends on the distance between x and the point you're going to. So you can think about how to do this for the problem in your homework, but that's all I wanted to say about that. So the next thing that I want to talk about is the formal definition of continuity. So now we have the idea of a limit. So limits, the idea is that these quantify local behavior. And quantify local behavior. No need to write anything else. Recall sort of the idea with limits, or not with limits, with continuity. The function does sort of what you expect at the point. So does what you expect. And so, if I want to say that a function does what I expect, by quantifying the local behavior, we do that through limits. So formal definition of continuity. So definition. So a function f of x is continuous at x equals c, so some real number c, if the limit as x approaches c of f of x, well, if that limit equals the function value at that point. So the function does what you expect it to do. As I'm approaching c, well, I'm actually going to get to the function value at that point. So recall our example from before. We had something like this. Notice that maybe if I call this c and this is I don't know, some number, and this is actually f of c up here, this function is discontinuous because the limit as x approaches c is this point. So this is the limit as x approaches c of f of x. This point in here is that limit. And as I'm approaching this point, I'm not approaching f of c. The function value is this point up here. And so this function is discontinuous. But if I remedy that situation and just modify the function at that one point, then now the limit as I approach my point c, I'm actually getting the function value at that point. The function is defined to be this y value at that point. So this is a continuous function, or at least it's continuous at that point. We say that a function is continuous without specifying a point. Continuous if it is continuous at, or just continuous, yeah, at every point. Okay? So that is the how we measure continuity using limits. So the idea of continuity, that a function should be doing what you expect, is now reflected in this limit notation, that as x approaches c, that for all the x values near c, f of x is doing what you expect it to do. It's approaching this value f of c. And when it doesn't, when I'm sort of approaching this value but my function is defined somewhere else, then I'm going to have a discontinuity. Okay, so that's everything I wanted to talk about in this lecture. In the next lecture, we will talk about properties of limits. They have a lot of really nice sort of properties that allow us to do computations with them, and we'll also cover some miscellaneous things to do with limits as well. Okay, I'll see you guys in the next lecture.